Hello everyone. I am pleased to introduce Bin Fan from Alluxio Inc. and Bin is a software engineer at Alluxio. He is one of the top contributors and PMC maintainer of the open source Alluxio project. Prior to Alluxio, he worked for Google to build the next generation storage infrastructure. He got his PhD in computer science from Carnegie Mellon University in 2013. He will be presenting a talk titled Spark Pipelines in the Cloud with Alluxio. Please join me in welcoming him.
Hi, good afternoon everyone. So as introduced, my name is Bin and I work as a software engineer in Alluxio. So before I begin this talk, can I see how many of you have heard or used the Spark before? Okay, I think most of it. How many have heard Alluxio or Tachyon? Tachyon is the username before. I see two. Okay, then you're definitely in the right room, so I can show you the case. Basically introduce what is Alluxio and how we can use Alluxio, integrate Alluxio use case, Spark use case with Alluxio, and in which kind of situations, in what kind of use cases you can gain performance benefits or other benefits. So this is the outline today. First, I will give I'll give an overview of Alluxio, and then I will go to some real organization or real company use case in S3. So before I really jump into any Alluxio related content, I want to go over what the big data ecosystem looked like in maybe 10 or 15 years ago. At that time, if you want to work with big data, this is pretty much the whole picture, the big picture you have. And this is two components. One is the Hadoop MapReduce, which is the computation engine you probably write up all your applications in. And the other component is the storage, and this is the Hadoop HDFS. So these two components are tightly coupled together. If you want to use MapReduce, you also need to use Hadoop HDFS. And HDFS is pretty much served for the storage engine as the MapReduce. So that's what it looks like 10 years, a decade ago. So what it becomes right now, let's take a look. So in Alluxio we call, let's take a look. On the bottom, on the top, there are all different kinds of computation engines. In addition to the traditional Hadoop MapReduce, and there are just more specialized or general computation framework like Spark, or more specialized for streaming like Storm, or for machine learning workloads, or for different graph processing like Presto. So these are different computation engines, and we call this to the north. This is the northbound. And to the south, there are also different kind of newly emerging different storage solutions, different storage systems. Like in addition to Hadoop HDFS, you also get those big data solutions from vendors like EMC, IBM, or even Huawei. And nowadays, even in this battlefield, there are also big players like Amazon or Google or Microsoft Azure who provides cloud-based solutions like AWS S3 or Google GCE. All kinds of these cloud-based solutions also comes into this picture. So we call this the south. Now, if you go from the south to the north, or if computation in the north wants to visit any data, access any data in the south, the path can be messy. Basically, you want to introduce anything new, you have to make very complicated integration. For example, you want to introduce a new computation engine in this ecosystem, then you have to, or if you want to play well with all your data, then you have to try to come up with every solution, the integration for every storage solution. And in the same case, you want to add any new storage solution or into any new storage cluster into your existing platform, then you have to make sure it works with all different kinds of computation you're using. So it's getting more and more complicated. So what we can do is, this is the motivation for Alluxio. We want to provide an abstraction. And this abstraction is between the computation and also the storage. So if any computation wants to access any data, you only talk to Alluxio. Alluxio provides the data abstraction. And if you want to add anything new to your deployment as a storage, then you just mount this mount your data through our provided interface. We call it adapter or end file system adapter to Alluxio. And it will shows up as one directory in the unified file system tree. So in this way, we can applications only needs to worry about where I access this data and doesn't really need to understand where this data is really stored or how this data is stored. All the complication is handled by Alluxio. The dirty work is done by Alluxio. And the same case, if you want to add any storage, as long as you interface with Alluxio, we take care of how you can interface with this storage using different interfaces we provide to the NORs. So this is very easy to add and remove new components in the system, and this decoupling of storage and computation provides you or enables you to scale your compute or scale your storage independently. Say, I want to buy more CPU because my workloads in the future will be more CPU intensive. Then you just maybe scale your northbound. You get more machines powered with beefy CPUs. And you don't need to really worry about the storage because this abstraction is, this storage is abstracted away. Versus in the previous days, if you want to go with the fully coupled solution and you buy Hadoop nodes, then you buy both CPU and storage. And maybe one is not really necessarily the bottleneck. So one more solution, one more benefits of this is once you are talking with the relatively slow storage, for example, the cloud-based storage, it's, the latency is higher compared to access the on-demand, on-premise data solution, then Alluxio also serves as an in-memory cache. And this is totally transparent to the application. And application on the first time will load data from Alluxio, and Alluxio will fetch this data from the cloud. And next time, when the application needs the same data, and Alluxio remembers this data because if it's hot, it's cached, and we'll just serve this data without talking to the remote cloud storage. So I will give a demo on this later. So basically, what I'm trying to say here is, by having another layer of interaction or another layer of abstraction here, we can make this ecosystem graph simpler and easy to maintain. Plus, we provide some performance benefits. If this is in-memory storage, it can help you. So in our mind, or as we see more and more, this is the next generation analytics stack, which works both for different kind of workloads we will cover in the later slides. For example, the big data workloads or the AI or machine learning workloads. We have also seen users doing deep learning, machine learning on top of it, and different LT to use Alluxio to maintain multi-platforms to provide the easiness of the data management. So now let's go to a little bit about Alluxio itself. So this is the open source project born in UC Berkeley AMP Lab. And this same lab also grows the famous open source projects like Spark or Oasis. So because this is the later project, if we just count the number of contributors in the first N months, in the first N months of the release in open source in GitHub, and we are one of the fast growing big data open source projects. As you can see, Alluxio is on the top line. We are about like close to be open sourced by 4 years, which is like roughly 45 or 48 months. And at this stage, we are our number of contributors, if you go to GitHub and check, is far more than these other projects on the same age. And also there are different contributors, as we can see from also all over the world, more than 100 plus different organizations and companies. And here I will just show you more about use case in the real world, in real environments, how people can benefit from Alluxio. So the first use case I want to share with you is in Barclays, which is one of the major banks in Europe. And in their case, this is a machine learning pipeline, and they are running Spark, using Spark to train their model. And the input of this model, training data, is stored in their Teradata. So the way it works is Spark kicks Spark jobs and read the training data from Teradata, and then use it, and then Spark jobs is called. And then later on for the next job, you do the same thing. You start a Spark job and then read the same data again. So sometimes, especially during the busy hours, the pipe between Spark and Teradata is kind of slow or can be very congested. And in this case, the Spark job just takes forever to load the data, although you just do this data loading again and again. So the solution they found is they deploy Alluxio co-located with Spark. And then before you do any training, you first load this or preload this data, prefetch this data from Teradata to Alluxio. And then Spark job will just keeps going repeatedly reading data from Alluxio instead of talking to the Teradata. And by doing this, their jobs can save a lot of time. So previously, it can take hours to finish because they waste a lot of time to repeatedly loading data. And now it can, for this phase, it can finish in seconds. So that's what they see, and they published as a blog how they can use Spark and Alluxio to make sure some jobs that doesn't really finish before or take hours, now they can finish this in seconds. They have a technical blog on this. You can take a look at the link. Can share data at memory speed because they both talking to Alluxio, they can both writing to Alluxio and reading from Alluxio. And what's more, the data from HDFS, now it can be cached in Alluxio for both read cache and write cache. And because the HDFS is remote, and sometimes the bandwidth is pretty limited during peak hours. So they have like promotion days, and when that happens, the connection becomes very bad. So what they do is they deploy this in the middle, and the Alluxio will help cache the data to hide the latency accessing the data in the HDFS. So what you see is 15x to 300x improvements in performance for this I/O bounded workload. The last example I'm showing here is from Guardant Health, which is a company doing genomics and also cancer research. What they have right now, or previously, right, is on the left, is they have the Spark computation jobs running, and it's reading their data from HDFS. And because they are owning more and more data, large scale of data, they're thinking, or they are on the way to move data to cloud-based solutions because that's considered as it's cheaper, more cost-effective. So they choose Minio, which is similar to Amazon AWS S3. And the problem is if you use your previous job to access Minio, and because the latency gets longer, you are accessing data in the cloud, you are fetching data, and you are pushing data over the wall. And this will create a lot of latency. So what they do is they put Alluxio in the middle and use Alluxio to prevent those I/O bottlenecks accessing the remote data. And in this case, they see orders of magnitudes higher performance. And we are we are having a meetup in the San Francisco area next week. And engineers from this company is going to showcase and also present with more details. Okay, so enough real examples. I want to dive into a little bit internal and tell you why Spark can benefit from Alluxio. And there are multiple reasons behind. The first reason is, for example, if you have Spark jobs running, and two jobs are, for example, are running on the same node, and they are reading the same data. And if you do the ordinary way, then you want to speed up, and you want to also speed both jobs, and you will end up caching the same data, two copies in two different JVM processes. So what's the problem? The problem is the more memory it's using by you're using on Spark, and the more pressure you give to Spark on GC and other related issues, or like just spilling data to your disk. Well, because there are two different processes, so by Spark, it's hard to share the data. You can just hardly share the data because there are two different JVMs. So what you can do is you can deploy Alluxio in the middle, and Alluxio is already an in-memory storage. So what you can achieve here is you store the data instead of in the Alluxio in the Spark heap on heap storage. You put it into Alluxio, and you let it do different Spark jobs, reading, accessing data from Alluxio. So in this case, they don't need to save the copy twice and spend resource for the same data twice. So I was working with some users in the community, in the Alluxio community, and they told me this is actually very common. For example, you have a user profile table, and a lot of jobs are reading this. Part of the job is reading the table, but joining with different other tables. So what they do, they found a way to optimize this kind of workloads is to push the common tables, common data set into Alluxio. So only one table is stored, only one copy of the resources spent. And this is one piece of the, one part of the benefit, where it is from. I will talk another benefit, potential benefit. That's about on the failure case. So if the data is really cached in the Spark JVM itself, so once the Spark, so because I'm pretty, if I'm a very new programmer in Scala, I may write some buggy code. So once my Spark job crashed, what happened is all the data within the Spark job will just be gone because this job will be canceled and the JVM will be killed. And in this case, if you restart the job again, first of all, if you kill the Spark job, even if it's the execution engine crashed, you will also lose the part you already cached in the Spark storage, right? So what you can do, or what you can do better is, what if you just offload the data into Alluxio space, because Alluxio is a separate process from Spark. Even your computation engine crashed, boom. You still have data in a separate process, which is Alluxio. And the reason this can benefit is because data should be really served from storage systems, which is separate, independent from compute. And by doing this, by separating responsibility, and on the failure case, you can just get a better story, because now you just restart Spark. So now you just restart Spark, and Spark can just access data from Alluxio without really loading the data and doing all this caching. Now let's go to a little bit more detail. How do you integrate a Spark? How do you use Alluxio with Spark? Well, it turns out pretty simple. Alluxio provides a file system interface. That pretty much means you interact with Alluxio through writing a file or read a file. That's the two ways you interact. So what you can do is, if you have a Spark RDD interface, you're using the RDD interface, the way you write RDD to Alluxio is to save the RDD as either a text file, if that's available, or you can do save as object file, and given this Alluxio path, that's it. It's pretty much like how you use HDFS, and in fact, you can do this because we provide a HDFS compatible interface. So if your application can talk with HDFS already, it's pretty much likely it can talk to Alluxio too. And it's even possible that you don't require any code change on that. For the read side, it's very similar. If you want to read a loaded file as the RDD from Alluxio, just .sc context.text file, or if it's in an object file, you do the sc.object file, and given this Alluxio path. So what if you are using data frame? Well, it's quite similar, as long as you give for example, if this file is in the Parquet format, and you want to load these Parquet files, and you first just upload this file to Alluxio, or load this file into Alluxio, and then give the path of this Parquet to data frame API, and you can just read this file or write this file. Okay, so given these two, like a rough idea about how Alluxio works with Spark, I want to dive a little bit more details or some performance evaluation to help you understand in which situation you see performance gain and which situation you may not really see. The experiment setup is we use Spark, and this experiment is done pretty much quite a few months ago. So it's still using Alluxio 2.1.2, and we are having 1.5 last month. And this is on a single machine on AWS, Amazon AWS, and we're trying to compare different Spark storage levels. If you read data which is already cached with Spark in different storage levels, and versus reading the same data from Alluxio. So dotted lines are the performance you're reading from Spark itself, and the sorted lines are the performance you read from Alluxio. On y-axis is the time you spend doing this, so the lower the better. And on the x-axis, we vary the RDD size. So for different RDD size, you may expect different ordering of this performance. And it's not surprising that if you cache the data into disk, the performance is worse. And it's very interesting that if the RDD size is kind of small, actually if you read from Alluxio, the performance is slightly worse than reading from Spark. But in that case, since the RDD is quite small, I guess it's not a very interesting case. So the interesting case is when the data size is growing, and you can see at a certain point, Spark, reading from Spark, cache data in Spark and read it back becomes actually worse. And the reason is, if you do the cache in Spark, it takes a lot of memory from Spark. And this will just pressure the Spark with a lot of memory pressure. So when that happens, we found reading from Alluxio is actually even faster. One interesting point here is to compare reading Alluxio from the text file and reading Alluxio as the object file. And this may surprise you that reading the text file is actually a lot faster. And the reason is, if you read from text file, the deserialization cost is smaller. And if you read from the object file, that can take a lot of time. So this is the one interesting find we have. This is another one. So if the RDD is stored in the S3 in the cloud, and now you want to create a new Spark context on this persisted RDD. If there's no Alluxio in the picture, it can just think this is very natural. It can take a lot of time to read this data back. So in this case, it's like 800 seconds. And in our case, if you use Alluxio in this picture, it can achieve even 16x speed up if it's a text file, or it's a 7x speed up. And the reason is because you don't need to talk to the remote and slow cloud. And this is the trend for reading the cache data frame, and the trend is very same. So I will just skip this. And also, this is also very similar experiment. But one thing interesting to note that we run this multiple times, multiple rounds. But we found without Alluxio in the picture, if your data is back in the cloud, the variation can be large. The performance variation can be large, because this is affected by so many factors, your network, or how the worker is working on the AWS cloud. However, if you just read Alluxio, because it's local to you, it's co-located with compute, so the performance is very deterministic. And this is very good for a lot of applications which requires a strict SLA. They are fine if you read slower, but they are not fine if the variance is large. So we definitely see some use cases are really, they want to use Alluxio to